Thank you, everyone, for coming to the Tulsa.net user group tonight. Michael Perry in from Dallas here in Tulsa, going to talk about identity, immutability, and polyglot notebooks. Michael, thank you very much for coming up to the Tulsa.net user group. I really appreciate this. You've been a longtime supporter of us, the group, and several of the people here. And I'm excited to talk about your book as well. You got a new second edition out.
Yes, indeed. Yeah, second edition of The Art of Immutable Architecture.
And I think there's a website for it.
There is, immutablearchitecture.com.
Awesome. Cool deal. All right. Thank you, Mark. Let you take away from here.
All right. Thanks, Sean. Yeah, thanks again for setting this up, for inviting me out. I really appreciate being able to see friendly faces and meet up with everybody. I want to share some of the ideas that I've really been thinking about for the past several years. Identity, immutability, and then there's this really cool tool. I don't know how many people have tried it out yet, called Polygot Notebooks, which let you run code in real time, interactively, and record. We kind of set up a document so that you can create documentation. Yeah, it's a really great way to demonstrate ideas. And so I've got a few things I want to show you there. So first of all, a little bit about me. I'm a director of consulting at Improving, offices all over North America, and author of The Art of Immutable Architecture, the second edition, immutablearchitecture.com, and author of the Janaga open source framework. So the reason I bring up Janaga is that the ideas of identity and immutability that I explore in the book really find their home in Janaga. So real quick, the Janaga replicator, this big old hexagon in the middle, that is an application agnostic backend. You might have heard of mobile backend as a service, that kind of a thing. So it's that. And you can see here we've got a couple of mobile applications. Suppose you're writing a Maui application and deploying it to iOS or Android, then it would be able to connect to the Janaga replicator. You don't deploy any code at all to the infrastructure. All your code runs on the edge. And you get local storage, authentication, and synchronization. Now, if you are not writing mobile applications, replace those with web browsers. And now you are using Blazor WebAssembly. So you are still delivering code to the browser, and you still have local storage on the browser and real-time sync on the browser. So it's the same idea for working. I would replace one of those with a web browser and keep the phone on the other one. And it's the same replicator for each. So you get all those working together. So I bring that up because this is really demonstrating the power of these mathematical ideas of identity and immutability. So let's jump to here. Let's talk a little bit about this idea of immutability. So what you see here is a binary tree. We've sorted a bunch of nodes into this tree so that we can quickly find something. So if you're looking for the number 17, then you start at the top, bigger than 12, so you go to the right. Smaller than 27, so you go to the left. Oh, there it is. You found it. Really fast search. So this is a great way to organize data. Now, if you want to add to this this binary tree, suppose you wanted to insert the number 22, you would do that search. Find it's bigger than 12, smaller than 27, bigger than 17. There's a place for it to go, right there on the right side of that 17. But that means in order to add it, you have to change things. You have to add a new pointer. You have to add a new link. And so imagine that you were using this binary tree on multiple threads. Now you have to lock it so that the other threads don't access it while you add that new node. Suppose you were using this binary tree on multiple machines. Synchronizing across multiple machines while you make this change, that can be kind of cumbersome. So instead of doing all that, let's make this whole thing immutable. Now, in order to add the number 22, we do this. I'm going to create a 22, and that goes to the right of 17. So that means I'm going to create a brand new 17 node that points to the 22, and it still points to the old 14. Now, because I've got a brand new node at 17, I need a brand new parent node at 27. Still points to 17, points to that new 17, but then now it still points to that old 32. And I continue on up the tree until I've also replaced the root. So I've got this brand new node at 12, and it's pointing to the new 27, but it's still pointing to the old 7. So if you look at the old tree, it still has exactly the same shape as it did before. If somebody is using that tree, they don't know that anything is different. That tree is immutable. This new tree is made up of 4 new nodes, and it shares all of the structure from the previous one that it came. So this is structural sharing. It's a technique for being able to evolve immutable data structures in such a way that you keep things safe, that other threads can continue to use the older version. And other machines can continue to use the older versions until they learn about this new thing. So no locking, no synchronization, just sharing of information. That's what we're going for, and that is the power of immutability. All right, let me, I'll end the show real quick so that I can bring up Polygot Notebooks. Actually, before we get to Polygot Notebooks, so first of all, I want to confirm that everybody's seeing the right thing on there. Let's now talk about identity a little bit. We will return to immutability. There's much more to say there. Wanted to give you a quick flavor though. So here I've got a brand new Postgres database. In fact, I'm going to create a database called immutability. I'll use all lowercase because this is Postgres and it likes lowercase. All right, refresh. There's my immutability database. Okay. Anymore? Okay. So we are using a database to build an application. Let's build an application that is all about courses at a university, which is this one. So I'm going to create a table called course. And so it's got a course ID. That's our primary key. You can see from that identity 11. This is an auto incrementing ID. And we've got a course code, the title, certain number of credits that it offers, and here we're declaring that course ID to be the primary key. So, oh yeah, that's the SQL syntax, not the Postgres syntax. Really neat. You know what? I have course ID. So hopefully Copilot will hop in here and say, okay, well, I'll do it this way. So let's go to Copilot over here, translate this to Postgres. Change identity to serial. Okay, that's it. Serial. Nope. It lied. There we go. Okay, so we've created that table. So now we have this this course table, and now I can insert into course. Let me refresh the public schema, the table. There's the course table. let's select, there we go. So we've got a table. So I want to insert some stuff. So I've got an application that that somebody can use in order to populate a course catalog. So let's go ahead and insert the chemistry course. And now we've got that in there. Okay, so my question to you, what is the identity of the chemistry course? I see some ones. Yep. Is 1 the identity of the chemistry course? The identity of this record, but the identity of the course is Chem 101. Yeah. Yeah, so we've got different ideas of identity. So sometimes when we're talking about the physical structure of a thing, then something like a file name or a location in memory or the auto-incrementing ID of a row in the database is the identity that we use for that location, that storage. But the identity of the thing, the domain object, that is something that most often comes from the domain. So this is called a natural key versus the primary key being a surrogate key, I think is the concept for. So we can also kind of see a clue that Chem 101 is supposed to be the identity of this course from this code that we wrote here. So we're saying where not exists an existing course. So if I were to run this again, then I would still just have that one method. So that is kind of a hint to the application that, you know what, I want Chem 101 to be the true identity. There's an even stronger hint that I can give, and that is to say, yeah, let's go ahead and add another example to our database. So now we've got a computer science course in there. So we've got those two. And so I want to give it this other hint. Let's see if this syntax translates. It might not. Another. Yeah, okay, that syntax translates. So now I've created a unique index on the course code. So that is a stronger indication that I want this to be the identity of a course. Now that that's more than just a hint to the runtime and to other developers. That yeah, do we have any water? I'm trying to get there. Okay. More than a hint to the runtime, the application developers that's the identity of the of that entity. Oh, it is also very important when we start to run this kind of code at scale. So think about what the computer has to do in order to accomplish this. It's going to first look in that table to see if that course exists. Then, if it doesn't, it'll do the insert. So if you do this inside of a transaction, then it will automatically figure out some kind of locking procedure in order to make sure that that truly happens. If it's not inside of a transaction, I think you might be running a risk there that you could end up, if you ran this at scale in parallel with the same ID, you might end up with duplicates. So having this uniqueness constraint turns that duplicate insert into an exception. And so it says, nope, try again. And then when it tries again, it already exists. And so it doesn't do the insert the second time. So you do a few things with the runtime and with the languages in order to express your intent about true identity. So now I've got a question for you here. So we have come up with these surrogate IDs here of 1 and 2 for the courses. What is the scope of that number 1? And how, if I were to run this application on a database and deployed to a different machine, maybe it's even in a different data center, would I expect to get these same numbers? Nope. Nope. So these numbers are very specific to the location of that database. They only make sense within that database, within that table of that database. So these I call location-specific identifiers. Whereas these can span the entire domain. You give that code to any database installed anywhere, and it knows that you're talking about the chemistry course. So those I call location-independent identifiers. So location-specific, location-independent, very important to keep separated while you are thinking about distributed systems and moving data around. So that's a bit on identity. Let's flip back to Visual Studio Code, and where is Visual Studio Code? And let me show you this really cool. Get out of the way for a second. This really cool thing called Polygot Notebook. So if you haven't installed these before, you can go over to extensions. Polyglot. You can search for Polyglot Notebooks. And this is an extension for Visual Studio Code by Microsoft that is based on the idea of Jupyter Notebook. So, so it's the same idea of being able to mix code and text, literate programming, as it were, in order to share your research with other people, or to share documentation, as I like to use it. So you can install Polygot Notebooks, and then you've got this little Command-Shift-P. If you say Polygot, we want to create a blank notebook. I'll create an IPYNB, and I'm going to create it using C#. You can see you've got all these different languages you can choose from, but we'll go with C#. And now in here you can write like var name equals Michael, and you can run that code. Well, it just assigned Michael to name. It didn't actually show us anything on the screen, or you can just have the variable or any kind of expression with no semicolon at the end, and then it will output that method. So then you can create new markdown, like so, and that becomes your documentation, and you can create new code blocks. So that's how we're going to be exploring this idea of immutability inside of a Polygot notebook. So let's go back to this idea of these immutable data structures. So here is a nice little immutable data structure. Nice little immutable data structure that we're going to use the C# record constructs to create. So that creates an object where we can assign properties through the constructor. Those become read-only properties, and so this is an immutable data structure. So I can run that, and we've got now this person. So I can even output the properties of that person, and so now we can see we created this immutable record. the name and the date of birth cannot change. Now, there are some properties that you might expect to have on a person that you might want to change over time. Like, for example, if you've got the int age. Look at that copilot making up the right code. That's kind of a cool implementation of it. It's almost right.
Yeah, that's usually the case.
Yeah,
Almost right.
So now when I run that, I can see now I've got a new age property. And the cool thing about that property is since it uses date time now, it's not even deterministic. I can run it again and it will give me a different value later. So I can kind of mix these behaviors into the immutable objects. So now if I were to share this person with another machine, it would compute age differently based on its clock. I wouldn't have to share that information, but I'm just sharing the immutable parts. So when we think about designing these distributed systems, we want to think about what parts are immutable, and those should be the foundation of our data exchange. So there's, by the way, there's my implementation. A bit longer, a bit more correct. Let's bring in. This is a really fun example. Let's talk about immutability from the perspective of a game, and this will help us to kind of think through real world applications. So what you saw me do here, this pound R, I just referenced the DLL. All of the code for this tic-tac-toe example that we're going to be walking through is on the GitHub repository that I'll share with you. And just compile it, and that DLL is there. So now it's available inside of Polygot Notebooks. So I'm going to create an empty game, and then I'm going to play in the fourth square. So go there. A little bit hard to see. Let me switch to light mode. Oh, there we go. Whoa. Yeah, now you can see the game board. So what I've just done is game.empty gives me an empty board game state, and then play 4 doesn't mutate the board state. It gives me back another game. So let me show you if I were to just do this. Boom, I've got an empty board. If I were to say game.play at square 4, it didn't change the game. It just returns another game. So I could say game equals game play 4. That basically creates that new game state and then stores that new object into the same game variable. So the variable has mutated, but the object itself has not mutated. I've just thrown away one object and replaced it with another. So that's what this tic-tac-toe thing does. Now, why would I care about that? Well, let's say that I want to continue this. So let's have the next player play at 1. This is 0 based, so that would be the top space. Now we've got a game state with that, and now I want to search for the best move. So what if I were to do a little bit of link here, and I just want to go through all of the empty squares. Well, let me just walk through this one step at a time. Let's start with just the empty squares. So now I've got a list of these are all the squares where somebody could play. Now let's, for each one of those squares, play that square and give me back the HTML. So now I've got the possible game positions after X has played in all those empty squares. Now, if I had actually changed the game state, then I would have X's all over this place. Actually, it would have switched over to O, and so it would have X, O, X, O, it would just be a mess. But instead, by using immutable data structures, I'm able to keep everything nice and clean and explore the entire space. So that is one of the really powerful things when you're now just sitting down and writing algorithms. Because just have something that's immutable, it's so much easier to reason about that. So,
Michael,
yeah.
please tell me the movie War Games came to mind.
Oh, of course. Of course. Yeah, the only winning move is not to play. But yeah, side tangent. The definition of game theory. I've never seen a clearer definition of game theory than that one scene from that movie. Could you destroy your enemy? Yes, we absolutely could. Do they know that? They certainly do. Then don't. Game theory. Beautiful. Beautiful. Okay. So now that we can produce all of these games, what I want to do is evaluate them. So here is this nice little evaluate method we can go through. And so I'll just go ahead and, I have this little immutable array thing. What's this immutable array stuff? Well, there's this nice little using system.collections.immutable. That awesome namespace that has things like immutable array, immutable list, immutable dictionary. So these are immutable data structures in .NET. You can just use them. So here what I'm doing is, given a game, I am going to check to see, does this game already have a winner? That's just a property we can inspect on the game. Has somebody won? If so, they're the winner. Are there any empty squares? Then if there are no empty squares, I'm going to return the symbol empty. So the symbol is either X, O, or empty. And so empty just means that it's a draw. So now the outcome, I'm going to go through all of the empty squares. I'm going to play that square. That gives me now a new game state. And then I'm going to recursively call evaluate. Then turn all those outcomes into an immutable array. Now I've got this array of the possible outcomes. And so here, if any of the outcomes are a win for the next player, then they have a path to a win. If any of the outcomes are a draw, then that means the opponent has a path to a draw. Otherwise, then it's the opponent that is going to win. So there's no win for the next player. There's no possible draw. The opponent is going to win. This is a mini-maxing algorithm. And it's really easy to reason about because it's all based on immutable data structures. So we've got that compiled. Now let's go ahead and run that algorithm. So I'm going to take this game, which we've already initialized it to have it's that game state right there. And we are going to play each of the possible squares and then evaluate that. Does that play lead to a win for X, a win for O, or a draw? And then we just run it, and we can see that if X plays in the corner, X wins. If they play in the opposite corner, they win. If they play on the side, they win. The only way that they don't win is they get to draw if they block themselves. So a really quick way to build something that searches the space and gives us information about what could possibly happen. And it's really easy to reason about because it's all immutable. Cool. Any questions or thoughts about immutability before we move on?
Can you apply this to the election?
Ah. Yeah. Let's return to the war games comment, and then from there we'll move on. All right. So now let's talk about taking this idea of immutability and applying it to building distributed systems. So let's go back to this idea of a course. So we've got this record that we'll define that represents a course. And so now I want the identity of that course to be the course code. So that means I can say the chemistry course is M-101. And so now I've got this record that has that that identity. Now, if I were to run this same code on a different machine, I would also get a record that would look exactly the same. So as long as I say identity means exactly what this record looks like, then I'm in good shape. If you were to use like the reference equal operator in .NET, you would get two different records. But if you were to compare, yeah, let's say that we've got chemistry 1 and var chemistry 2, but they have the same identifiers. Then if I were to say chemistry 1 is equal to chemistry 2, double equal like that, what do I get? Do I get true or false? True, yes, because .NET, in order to compare records, compares all the values. So it's doing this value-based comparison versus if I were to do that reference equal actually maybe yeah. Oh, equal. Yeah. Okay, object reference equals chemistry 1 chemistry 2. Got it. Okay. So object reference equals chemistry 1 chemistry 2. Now we get false because these are two different memory locations. So this is kind of like the memory location is like the surrogate key. It's you know like some fake identifier, but the true identifier, the true identity is this value comparison. So let's focus on value comparison as the identity of records. Now, if I want to name these courses, if I were to here, let's redefine the course record to have a code and a title. So what is the problem with that data structure? Yes, exactly. So we've got two things that are both Chem 101, but we've given them two different titles. So are they equal? No. So when we're using immutable data structures, we want to take the identity of the thing and make that the whole thing. We don't want any parts of an immutable data structure that are not part of its identity. So we don't want any parts of an immutable data structure that are not its identity. So since we mix name in here, and name is not part of the identity of the thing, now the immutable data structure doesn't behave the way we expect. But I'm sure you're asking, how do I record the name of a course if I can't include the course name in the thing? So let me go back to this definition. Boom. I've got that definition for course. Now I'm going to have another record that I will call course name. So for a given course, this is going to be the name record. So let's set up those definitions. And now I could say that chemistry 1 and chemistry 2 are going to be exactly the same shape, so therefore the same identity. But then I want to call one of them intro to chemistry, and then I might have another name that's basic chemistry. So now let me just look at the structure there, and so I see I've got this this object that has as one of its properties another record, the course, and so I can think about that other record as some predecessor to this one that says that is the course that I'm talking about, and now this one asserts the fact that the name of that course is Introduction to Chemistry. Now, so I've gained the ability to use an immutable record as an identity. I have now lost the ability to know what the name of this thing is, because one fact can assert that it's Introduction to Chemistry, and the other one can assert that it's Basic Chemistry. Is there any way for me to win that back? So let's go back to first principles. This is, we're just thinking about what is actually possible in information systems. I've got two different machines. They both have their own databases, their own data stores, and they're both accruing information from whatever users they have, whatever systems they integrate with, and they're exchanging that information with one another. If one of them learns the name Introduction to Chemistry, and the other one learns the name Basic Chemistry, is one of them wrong? Does it even matter the order in which that happens? So if you were to look at the wall clock and say, oh, that one occurred 5 seconds before this one, is it really last writer wins? If they didn't exchange information in that time, does time really matter? So I assert that you cannot know the one true value of a property in a distributed system. Properties don't have single values. They have values that are just sets of possible values, candidate values. Now, in order to make this a little bit easier to see, let me bring in a NuGet package. So NuGet Jnaga. And then I will say using Jnaga. Run that. So this is also a really cool feature of Polyglot Notebooks. You can install NuGet packages. So now we've got the Jnaga package in there. Let me redefine the course, but now I'm going to be using fact type, and I will call this school.course. So this is going to be public record course, and it'll have a code. So now I've defined that type. Let me also go ahead and define the course name. I like to use this notation where I've got the namespace, the entity, and then the name of the property. So we will have the course name be this other thing here. So now we've defined our data structure. So let's create some instances. So I've got chemistry, and then we'll have the chemistry name. Now I want to see what that looks like. So in order to do that, let me stick another code block right here. I'm going to create a Jnaga client. boom, boom, just like that. And so now I want to take these objects and put them into the Janaga client. So that's basically my own local repository. So I'll say await Janaga client dot fact. So put that in there. And so now I can say Janaga clients, please render facts. And I want to Janaga client does not. Oh, that's because there's another package I need to include. There's a NuGet package just for notebooks. So Janaga notebooks. So now with that NuGet package, it can do the same thing that we did with the HTML up here. So it can render objects as HTML. So now that I've got that, I have render facts, and I can, let me see if I can zoom in on that a little bit. I can see this object structure here that's showing me that I've got a school.course with the code 10101 and school course name with the name Introduction to Chemistry. That points up, that points back in time to that predecessor, that identity. So let's see how that is helpful. Let's suppose that now I want to figure out what is the name of a course. In order to do that, I'm going to say name of course. I'm going to create a specification. So given a course, I want to match course facts. I will explain in just a second who would be the facts thing. So I want from the name in facts of type course name. Good thing Copilot knows me and remembers how to write a specification. So I'm looking for names in this type course name where the name.course is equal to this course parameter. Then once I find that, I will select name. Let's just do select name for right now. And that gives me a specification. Now I can execute that specification. And I will do await Janaga client.query name of course starting at this chemistry course. And so show me what those names are. And I get back this collection of course names. Or if I really want to see it better, I can say Janaga client.render facts. I can go ahead and render out these first names. And I get that graph. So that that lets me use LINQ in order to query these directed acyclic graphs of immutable facts. And I can start from one and join to the others in order to figure out what is the shape of this graph, what do things currently look like. So now if I get to this point where I've said, you know what, it's not Introduction to Chemistry, it's going to be basic chemistry, I'll go ahead and run that. Now if I were to rerun this, I now have two course names in my repository that refer back to that same course identity. So this is very similar to those two machines running their own different databases, integrating with different systems, and they come up with two different names for the same thing. Which one is right? How can you tell? Let's modify things a little bit to make it possible to tell, at least to some degree. So I'm going to go up here to this course name facts. Let's change the structure a little bit. So in addition to the course and the name, I'm also going to have an array of course names that I call prior. Okay. So now when I set that name, basic chemistry, I can use the empty array, and that tells me that the prior collection is empty. In fact, I'm going to clear out the data that we had since we changed types. I'm going to clear that out by creating a brand new Java client. So I ran that. Okay, now we've got the chemistry fact and the chemistry name fact that refers back to Chem 101. Now, what if I wanted to change that name? So I'm going to have a new chemistry name. And so this is going to be Introduction to Chemistry. And so it's going to list chemistry name as the prior value. So let's go ahead and run that. And then let's see what this query gives us. So this query is showing us that the shape of the tree is that I've got the course, Chem 101, and then the course name, Basic Chemistry, pointing back to that one. But then there's another course name whose prior is this name here, and that's Introduction to Chemistry. So if I see that graph, can I tell what the current name is? That's going to be the leaf of the tree. It's going to be that very bottom one. That's the most recent one, because it replaces all the prior. But
so this structure would let you point with a course name to a course name that belongs to a different course.
excellent point. Yes, this structure would allow you to do that. It would allow you to point to a course name that actually points to a completely different course. Yeah, so there is a way that we can modify this this specification so that we exclude those anomalies. So if I say, well, yeah, I'm going to do that right after I do this part. So, excellent.
Stop skipping the line.
Let me get through here already. Yes. So I really want this specification to limit it to just the leaves. Just tell me the actual course name. And right now, this is giving me all of them. You can kind of see a slightly darker border around these two. That's telling me that these are the two that are in that collection. If I just said names here, you can see that's got those two names there. But I want to filter out those that are not the leaves. So I can tell it's not a leaf because there's another name that points back to it. So here I'm going to say, and there is not facts.any course name. We'll call that next, such that next.prior contains this name here. Okay, so if there is another course name, call it next, like this one right here, there is a course name next, whose prior contains this one. So because of that, we want to exclude it. So now if I run that, the graph will look the same, but notice the dark border has gone away. So it's showing me the full graph because it has to show me the full graph for me to understand this one fact that it's talking about. But in fact, that is the only fact that's in the collection. So this specification, this tells me the current state of of the world. Now, it's still possible for this specification to give me back multiple results. For example, if on one machine somebody had changed from basic chemistry to introduction to chemistry, and then on a different machine, yeah, somebody said, yeah, chem party. Woohoo! That's good stuff. Yeah. Now I get this shape where on one machine I changed it to introduction to chemistry. On another machine, changed it to chem party. Those now are the two candidate values. So the core idea here is that if somebody makes a decision with prior knowledge of somebody else's decision, then theirs is the new decision. But if they didn't even know about the prior decision, then let's not just clobber it. It's not less right or wins. Let's not just take one as the value. Let's honor all those other decisions that were made without anybody else knowing about that. And once all that information moves around, then that's going to be the state of the system. So if you've got a multi-user or a multi-user system and people are editing the course catalog and you record the course catalog like this, you can see that entire history of the decisions that people have made. And you can see if you've got more than one result from a specification that there has been a concurrent edit. And you can see what the candidate values are. So you can just say .select and name and say, yeah, those are the candidate values. Let me go ahead and present those to the user, say which one of these is right, and we'll pick it. Oh. Mm-hmm. Yeah, this is reminiscent of Git. Each one of these is a different branch. A branch is just a pointer to a commit. So that's a commit. That's a commit. These two commits have the same parent, so they branch from that same point. So now in Git, when you say, oh, somebody else has made a change to this file, I've made a change to the file, I want to have both of those changes, you need to merge. How do you do that? So let's say that I've got this collection of names, and I want to fix it. Yeah, this chem party thing. Somebody was just having too good of a time. That's not the actual name. Let's say we're going to await another client dot fact, and this is going to be a new course name. The course is chemistry, and the actual name is Introduction to Chemistry. And now the prior collection is this collection of names. So I'm going to say names dot to array. Let's zoom out a little bit so we can see that whole line. So that creates a fact that has two prior predecessors. So I run that. And oh, I didn't have the semicolon, so it actually showed me the output of it. That was kind of cool. But now if I come back here and I run this specification, run it. There we go. Now it has merged that graph back together, and I have just one. Yeah, that's graph. Yeah. Yeah, it has these little artifacts. So now names has only one value. That means the concurrent edit has been resolved. I'm avoiding saying conflict. I say concurrent edit. Yeah, the reason for that is I'm using a definition of conflict for which conflicts do not arise in this kind of system. This is using what's known as a conflict-free replicated data type, CRDP. And it's conflict-free because it mathematically proves that conflicts cannot occur. What's the right definition of conflict? This wasn't a conflict because if you were to give this state to two different machines, they would look at it and say, yep, that's the same state. We have two possible candidates. No conflict here. That's what the graph looks like. So it's an eventually consistent kind of a definition of conflict.
So, Michael, earlier when there were two names, you could look at both of those names and make some sort of fact. Which one is correct? Would it be valid? Because you also said earlier that you don't want anything that's not part of the identity of the object to be part of it. Would it be these facts so that I can see introduction to chemistry was, some admin on such and such date, and Chem Party was some knucklehead.
Yeah.
Couple days later.
Yeah.
You're in college and you got the password.
Yeah. So the question is, given that we don't want to have anything that's not part of the identity of the fact in the record itself, would it be valid to put auditing information? I tend not to put auditing information in there for exactly that reason. But it's not invalid to do so. It's just a choice that now you have made that auditing information part of the identity. So because in this model, I'm not using the time or the username. That means that if some other user at a completely different time were to make exactly the same decision, so set the property name to exactly the same value, then they would just come up with the same fact, and it would look indistinguishable as anybody else. But if you do put that auditing information in there, then that creates a concurrent edit when there didn't need to be one.
So if somebody spams the rename button instead of being identical facts, which results in the same identity, it would be slightly different facts for only the auditing information.
Right. Yes. Yep. Yeah. Somebody slammed that button multiple times. You get multiple instances of that record where only the auditing information is. So yeah, there is one last little thing that this unlocks, and this part is really cool. So I have here a little program called the catalog. So this creates a Janaga client, just like we saw in the notebook, but this time it sets the HTTP endpoint to this URL. So we've got localhost 8080 Janaga. If I come over here, I don't have one running. Well, let me fix that. I'm going to go up to janaga.net, and in the docs, I can set up my own replicator. Well, let's create a replicator using Docker. So I'll go to a terminal. And here I have, I'm pulling the Janaga replicator Docker image, and then using Janaga run to start a replicator called my replicator. And if this, I might just need to, oh, okay, there it is, it's running. Okay, so now I've got a replicator running at 8080. This is just a piece of infrastructure. It's a container, knows nothing about my application, and it's up there and it's running. So here I told this, okay, connect to that replicator, and now I want you to run this specification. Given an institution, I want to match all of the courses in that institution. Then for each course, give me the course titles. There's that specification that we were just talking about for the course title. Also give me the number of credits. There's another specification there. And that gives me back the course catalog for an institution. Now I'm going to go ahead and create an institution using some institution identifier that I pulled from a database somewhere, which happens to be an identifier that some College of Law has for this school here. And then we subscribe. So whereas before we were doing a Janaga-find.query, now we're doing subscribe. And so that's going to call us back every time we've got a brand new projection. And so I'll write out that I'm going to go ahead and insert that projection. Furthermore, since title and credits are specifications of their own that are created observable just for those child specifications, whenever we get a new title or a new set of credits, then it'll call us back on these small little lambdas, and we'll do an update. And so in this way, this code will keep a course catalog search index update. So let me run this. I'm going to come down here, school catalog. Let's start a new instance. Yeah, without debugging. Okay. So here we are, receiving courses, press any key to stop. Now this is using a model. So I'm going to go to the model for this application. So we've got the institution, the course, the title, the credits. I'm going to pop those into my notebook over here. So now I've redefined my my model. Looks very similar to what we were going through before. And then here I'm going to say let's redefine Janaga clients. And this is going to be Janaga client.create, but I'm going to have the same options as I do up here, where I set that URL. So now the Janaga client inside of this notebook is pointing to the same replicator as this program running down here. So now if I create a new course, well, this isn't going to quite work because first I need to create the institution. Let's copy that institution in here. Here's the institution. So now I've got that institution, and so course now takes the institution as the first parameter, and then the code. But then from there, the model is the same. So let's go ahead and create that. Oh. Janaga client. There we go. Boom. And that converts from. Oh, okay. It got all kind of messed up. Well, let's come down here and see if we can run it down here so that we know what I'm talking about. Those are my types. Ah, okay. Yeah, thank you. There we go. Okay. All right. So now inside of the notebook, I have created these facts. Some other process received that information.
Change data capture.
Yes, exactly. And if you were to deploy these to different machines, it would still do that. And let's kind of come back to here. That's because of this little thing in the middle. This is a replicator. That's what a replicator does. You push facts into it. Somebody else has subscribed to a specification. It says, oh, I know what would satisfy that specification. Here you go. And it pushes them down to the subscriber. So if you've used something like mass transit or in-service bus in order to build a distributed system, then you've had to set up messages and you've had to maybe manage keys. Mass transit will create keys for you. It's pretty cool. But still, there's a lot of work that you have to do in order to figure out what are the right messages, who should subscribe. This is all derived from specifications. That's the Polygot Immutability.
So if you were to stop this process and restart it, would you get that same set of insert, update, update?
Excellent question. Let's try that. So Control C, stop it, and then let's go back here and start it again. How do you do it? There it is. You get the same thing again. Yeah. So a replicator is not just a queue that forwards the message and then forgets about it. It's also the database. So it stores that history. And so different clients can come in and subscribe to their subset. This is a directed acyclic graph. You can just subscribe to a little subset of it. What you're interested in, and then it will project that into the information that you are interested in.
Okay, so on the thinking on like financial transactions, right? Don't hit the button twice, that kind of thing, right? Okay. I'm gonna try to think while I'm saying this out loud while I'm trying to think. If you've got multiple clients and you want to react, and so you're going to subscribe to a model, and I want to capture some financial transactions based on that, what I'm subscribing to, right? How do I know when I'm done? Do I subscribe? I get done with maybe some processing, maybe it's to the credit card transaction, then I'm done with that one, and I subscribe to something else.
Okay.
Or do I want to keep subscribing to capture the whole stream of things?
Yeah, good question. So when do you know you're done with a subscription? It's in here. Here's the code. Okay, so this subscription, I guess I could have just hit a key instead of simple key. Anyway, yeah, this subscription is going to keep running. It's a live connection to that replicator until you call stop on the observer. And so you start your subscription at one level higher than what you're thinking. So yeah, Sean was asking about how do you know when you're done with the transaction? Do you stop subscribing and then now you subscribe to something else? Subscribe one level higher. If you're at a financial institution, you're going to subscribe at the level of the bank. And now you're going to receive all of the transactions for that bank.
Or maybe for that branch office.
Or for that branch office, yes.
Okay.
Yeah. And you just keep on receiving them. And so it's going to be different accounts each time. The accounts themselves are going to be back, so they're going to be predecessors in this graph. And so you might have an on-added that now looks for transactions for that particular account. But you receive those, you handle them, and you just keep them on.
Okay, and then let's say the client falls out for whatever reason. Obviously, the replicator got the database, it's going to get a repeat of that information. But let's say if I get 99% done, do I have to start all over? Or can I go back up a few steps and go, nope, this I've already processed this side. Oh, but here's the 5 more I didn't get.
Yeah. Okay. Excellent question. So if it bombs out, you have to start over. We've already just seen that if you start the process, you're going to get history from the beginning.
Sort of. I mean, because
like here, we did not get basic chemistry because Ken Carter replaced it. And And so the second time through, it knew that basic chemistry was no longer something that satisfied that specification. So it didn't send it to the second. That's the key to avoiding that replay. Is now when you process a transaction, you then create a fact that is a successor that says, I processed this, and now your specification includes the clause where not exists process.
So you save a fact as a cursor back into the model.
Yes.
Back to the replicator.
Yes, so that goes back to the replicator. That also stays on your replica. So the other thing that you can set up here is, where is my database? Like, where's my SQLite database? Oh, it's right here. So I'm saving a replica of everything. So you've got a replica of everything that that you've received, that you've done. You set that up to the replicator, so so it knows, and it's not going to send that information back to you. And you will often have those successor facts not just as cursors or little placeholders that things have been finished, but also continuations of the conversation. So it's like, okay, I processed that, and here was the result. And now somebody who initiated that process is subscribed and listening for the continuation.
So if I've already processed the transaction, I say my system bombs, or at some point I need to catch that there was an addendum that somebody else might have made, either seconds later or a day later, something like that. Now there's an addendum. Whenever it retrieves, it will retrieve just like that, but it will retrieve the insert in the latest update, even though I've already processed it. Now there's something else to capture about it.
Yeah. So there's an addendum that somebody else does, much later. Basically you are in complete control. You design the model to represent that domain, and you put those clauses into the specification, and then you get that behavior.
Okay.
Yeah, that right there is the power of mathematics. That is, we can take these specifications and work on them as if they were equations. They basically are equations. They're algebra, and you can manipulate that algebra in order to convert a specification into a feed. You can convert a specification into an inverse.
You can easily create a new fact that returns back all the different various titles so you can see the credit history of the transactional history.
Right, yes, yeah. In order to see the entire history, you just eliminate this part of the where clause, and now you've got the full history.
Because maybe that client is an auditor.
Yeah.
He needs to see all the details.
Exactly.
Okay.
It seems easy to accidentally the whole thinking database though.
It is possible to do that. There are other guardrails that I didn't talk about here that will help in those situations. In that particular situation, there's a distribution rule, which is really there for security, for privacy. So you set up a distribution rule that says these people are allowed to create these specifications. So you craft those carefully. You don't want to expose too much for your distribution rule. That's a security feature. But then once you've got that in place, then somebody creating a client can't set up a specification that gives them more information than you want.
So someone couldn't happen to use replicator.
Right. Yeah. So yeah, you don't deploy code to a replicator, but you do deploy security rules, distribution rules, authorization rules, authentication mechanisms, those kinds of things. So yeah, kind of wrapping it up. This picture right here, this is what you can accomplish when you now take this idea and you put it into practice. So this is an imaginary, fleshed out course management system. So here you've got web applications, and they've got these little hexagons on them because they have their own little replica, their own little cache right there at the web server. So these are serving up an application that students can use to register for courses. Yeah, that's true. Back here, you're doing some legacy integration with other schools and exchanging course information via FTP. So you've got a little Lambda function that's running Janaga on the edge and talking via FTP. You're integrating with partners. You've got another one with its own little replica, and it's some SOAP interface. And you've set up some distribution rules so that you limit the amount of information that flows out to that replicator. Up here you've got our indexer function that we just looked at, indexing the course catalog, so that then the browser application can use that course catalog to quickly look up a course, but then they can register for it through creating their own tags. Everything in the middle here, everything in the middle are just these hexagons, just replicators. No code in the infrastructure anymore. You're not writing any more web applications, web APIs. You're not writing schemas that you deploy to a database. You're not setting up bespoke named queues. You are not putting any of your domain knowledge into the infrastructure. Infrastructure is all domain agnostic. All of the domain knowledge is at the edge. And then it just figures out how to route information through the infrastructure. That's what you can And that's the power of mathematics with identity, immutability. You can use these tools with the infrastructure that you currently have. You can bring in Janaga and play with this new vision. Reach out to me, whichever way you want to apply these ideas, and let's make them happen. Thank you very much.
No, half your brain's trying to conquer the world with this.
Like, okay, which project, which client am I going to use this on? If you have a question, one, do you have a TypeScript client?
Yes, that was the first one.
Oh, that's right. I remember. Okay, and then the second question is how do we deal with that testing problem of name points to course and to predecessor from other courses?
Oh, right. I did say that I was going to get back to that. Yeah. So right here. Yeah. So this is where you would say you're really just worried about next. So you would say and next dot course is equal to course.
But isn't that a flaw in the model though? Doesn't the model allow you to represent an invalid state?
That is true. The model allows you to represent an invalid state. There are constraints that you would like to apply that you cannot apply. In a lot of cases, maybe not this one, but in a lot of cases, those constraints that you cannot express are also the constraints that are difficult to implement in a distributed system. Those are the constraints that require locking, that require centralization.
Well,
but in this case, that's not true. But
what I want is an outgraded data type where it either points to the course or it points to a set of predecessors. Mm-hmm. But even at that, though, the set of predecessors can still be from the course.
Yeah. I think that is achievable. I haven't built that into Janaga, but I believe that could be done. That doesn't violate any of the math that I can look at. Yeah, so let's work on making that happen.
There's a couple of questions that came in.
Oh, excellent. All right. Okay. All right. So does Janaga run on platforms other than .NET? It also runs in TypeScript. So you can use Janaga with React is the best way to do that. I will be supporting React Native very soon. But yeah, right now .NET and TypeScript. And I think we lost my video, but Yes, we still have the audio running here. So why does every property have to be part of the identity? 2,500 years ago, Aristotle identified a distinction between essential and accidental properties. Is it necessary to get rid of that distinction? That is a really good point. Well, it's from Randy, of course it's a good point. Yeah, let's have a conversation about that. The reason in this domain that it has to be part of the identity is that I'm using the set of values and predecessors of a fact as its identity. What I'm really doing is I'm taking that and computing a hash, so it's a consistent hash. If you were to create the same fact with the same predecessors, you'd get the same hash. And so that not only makes the code work, that also makes the math work. And so now I can prove a whole bunch of things. I can derive feeds from specifications because of that decision. So could there be a way to solve the problem by making a different decision? I don't know. That's worth exploring. All right. Any other questions?
Nope. Those are the last ones on the.
So I'm just thinking about it because it's all mutable, so nothing goes away.
Mhm.
Is there a certain scale, a trillion records, that we way?
Yeah, good question. So performance at scale, is there a limit? I have not tested to find that limit yet. That is one of my my projects. I can say that the so if you were to compare this with the way that you would write an application using the traditional infrastructure that you use, you end up with the traditional style fetching information more than once. Whereas if you've got replicas, then it gets replicated and you run all of your queries locally. So so in general, for the kinds of things that you would ordinarily do, there's an argument to be made for this being having better performance in those cases. Now, there is the issue of, well, this is immutable. These things never go away. What do you do about that? There are there are patterns that you can apply in order to keep to keep history segregated. One of the patterns that I love to apply is called the period pattern. So you define in your model a period that is meaningful in your domain. So in the school example, it'd be a semester. And so then all of the facts, like for example, the course offerings, have predecessors to that semester. Maybe you find even a way to make the course catalog itself, even though you offer those courses semester after semester, tie those into the semester period so that then you would create a brand new course fact for the brand new semester, so that if you do retire a course, then it's no longer in ongoing semester. And now you can take a prior semester and all of its successors and put that on ice and archive that information and only keep the most recent 3, 5, whatever semester.
You're doing data partitioning according to the domain.
Yes.
Okay.
Yes. According to the domain.
Yeah.
But yeah, I definitely do want to put this to its limits to see what it's good for. I suspect that somebody really skilled at Kafka, working at Netflix could do better than this. Absolutely. I also suspect that the kinds of applications that we tend to build in Entity Framework with an ASP.NET monolith could be improved.
Cool. All right. Thank you, Michael. Greatly appreciate it. Yeah, please. I want to encourage everybody to check out immutablearchitecture.com and go to Amazon right now. Search for The Art of Immutable Architecture, 2nd edition by Michael Perry. Grab that book. I promise you, it is absolutely worth its weight in gold. If not more. How's that? So, all right.
No, it's a heavy book.
It is a heavy book. I mean, that's just help with that one.
Yeah, and somebody in this room is going to lug home a copy of this book. Is that your copy or is that mine?
This one's yours.
That's okay.
To give away. So we will give this away here in just a moment. So with everybody online, thank you all for coming out. Stay tuned for some emails coming out from the next meeting that we will do coming up soon. And so stay tuned for that. With that, I will bid you all farewell. See you next time.